Hi, and welcome to another episode of Autodesk Simulation TV, Simulation in Action. Today we're going to be talking about simulation Moldflow birefringence. My name is Matt Jaworski, and I'm a technical specialist here at Autodesk. So for the problem description, we're going to do an exercise that looks at performing a birefringence analysis on a Fresnel lens. Fresnel lenses are used to take the bulk out of larger lenses, and it essentially breaks it down into several different types of lenses on a part. Some of the key learning objectives are to first define what is birefringence and some of the terminology that goes along with it. Then we're going to look at setting up a birefringence simulation. What do we need in terms of mesh, material, and process conditions to set up an analysis? And then finally, we're going to look at some analysis results to see what to look for. So a good place to start is, what is birefringence? And birefringence is a change in refractive index of a polarized light that passes through an object. So typically this is a clear plastic part. And you see we have some utensils in the picture on the screen. And birefringence is really caused by the difference in refractive index from a section of the part to another section of the part. So what is refractive index? Refractive index, also abbreviated as N, is a property of a material to slow down light. So as you see in the image off to the left, when the lens material has a refractive index that's greater than air, it causes it to converge. And when we have the opposite, it will diverge. One other thing that we have to talk about are some different terminologies to give you a background on some of the results that we plot in the Moldflow software. So the first one's called retardation. And if you have a light source, a directional light, and it travels through the plastic part, retardation is the difference of the length of the optical path. So as you see in the image above me, we have a light source coming in and taking two different paths. One, it's going to have a little bit more distance, so that would cause it to have a different length or optical path going through the part. So it is direction dependent, and it's equivalent to how far out of phase the two components of the light wave are. And they can be different at different points in the object and even through the thickness. So retardation is defined as birefringence times the thickness. We also have a terminology called phase shift. So phase shift expresses the retardation relative to the wavelength of a light, typically a green color light. So the unit is represented in radians or degrees, and it depends on the direction of the light. It can be different at different points, as we discussed before. You can see birefringence bands in a cross polarizer when the phase shift is greater than 2 pi or 360 degrees. And this can cause double images like the image you see above me. So phase shift is defined as 2 pi over the wavelength of light times the retardation. So why would we want to run a birefringence analysis? Birefringence can lead to many different part defects. The first one being blurred images or double images as you see through the part, or it may give us poor optical performance of parts, for instance, a lens. And birefringence is commonly used as a method to analyze stresses experimentally. Birefringence is strongly influenced by the manufacturing process. For instance, in injection molding, birefringence can vary by a factor of 100 or more for the same material inside of one part. And birefringence is influenced by the geometry of the moldings, the type of runner system that you're going to use, the position inside of the molding, and the parameters of the molding. So as you set up the machine, things like injection speed, packing time, packing pressures, temperatures in terms of melt and mold, and cooling time all have an influence. Birefringence is really related to molecular orientation. And we have two things that we're looking at for clear plastic parts. The first one are elastic deformations. These are determined by the residual stresses inside of a part, and we use a stress optical law to solve for these. Also, flow orientation, which is caused by the history of the material orientation during the injection molding process. We have viscoelastic deformation, or so-called frozen-in stresses, and we determine these by using a generalized Kelvin-Voigt model, which accounts for temperature shift, normal stresses, and the rotation of the polymer. Now let's take a look at how to set up a birefringence analysis inside the Moldflow Insight software. First, we need a 3D meshed part, and that part should have at least 10 layers of elements through the thickness as a minimum. And this is to pick up what happens through the thickness. We also need a material that has optical properties. If there's a particular material that you use that's not in there, Autodesk also offers material testing services in order to get those properties to put into the software. Then we're going to set up the analysis sequence. The sequence has to include warp analysis. So it can be fill pack warp or cool fill pack warp. It just has to include warp because that's where birefringence is calculated. When you want to do the birefringence analysis, inside of the process settings window, as you can see in the image off to my left, there's an area where you can check off a box for birefringence. And that's needed in order for the analysis to run the birefringence calculations. So now let's set up an analysis of birefringence inside of the Moldflow Insight software. So the first thing that we need to do is go ahead and import a model. So in this case, I'm going to import a part that is in an SAT format. So we'll go ahead and open that up. And we do need to run with a 3D mesh. So we can import as dual domain, make sure that the dual domain is a watertight model, in that it doesn't have any defects, and it has a nice low aspect ratio and everything that we need to have a good meshed part, and then convert it to 3D after. Or if we're confident that the CAD model is of good quality, we can convert it to 3D right away. So I'll go ahead and do that. Now the part is read in. And the first thing that we have to do is again mesh the part. So we're going to go in and create a mesh. We're going to try to pick a global edge length, and the preview's a nice way of looking at about how big each element is in terms of a global edge length. And we normally want to use a rule of 3, so have 3 elements across drastic changes in thickness. And I see with the spacing in here that looks like that this is going to give us about what we want. So I'm going to just round this up to 0.15 inches. And then I'm going to go in and start to look at some of the other options. There's not too many curved features on this part, so I'm not going to turn chord angle on. And what I'll do is I'll go to the Tetra tab and make sure there's at least 10 layers of tetrahedral elements or 3D elements through the thickness of the part. And then I'll go ahead and mesh. Now we get the indication that the mesh is complete, and we can move on to the rest of what we need to do to set up a birefringence analysis. Now I'm going to search for a material that contains the birefringence properties that we need for the analysis. So we can double click on a material to search, then click the search button, and then what we need to do is add a search criteria for the birefringence properties. So I'm going to scroll through the list until I get down to stress optical coefficients, and then I'll add that to our list. And I'll just make sure that it's at a very low value, and then make sure it's at a very high value. And that will search for all the materials that have coefficients in for birefringence. So in this particular case, I'm just going to pick a material and select it for use in the analysis. Now if I look at the details of the analysis itself, there is an optical properties tab that allows us to see some of the different material properties that are needed for a birefringence analysis. Now that we have the material selected, we can also go in and start to set up the analysis. So an injection location is needed. So let's go ahead and place one of those on the part. and then I'll finish that selection. We also need to have some process settings and turn on the Birefringence Analysis. So if we go under Process Settings, the option at the bottom of the first Process Setting wizard screen is Birefringence Analysis if material data includes optical properties. So we'll go ahead and turn that on so it knows to run the Birefringence Analysis. Now we're set up to run. We could add a runner system if we wanted to, or multi-cavity parts, but we have the bare minimum that we need to run a Birefringence Analysis with an injection location, process settings, and the option checked off with a material that contains stress optical coefficients. Now I opened a different part here that has a gate location, and I added a runner system to the part and meshed it a little bit finer than the last model that we looked at. What we're going to do next is take a look at some of the results that you can get from an analysis that would be useful for somebody designing an optical part. One of the first analysis results that we can look at is volumetric shrinkage. Now, plastic materials can shrink as much as 25% after you heat them up and then cool them down. So those large changes in volumetric shrinkage are something that we use the packing phase of the injection molding cycle to compensate for. Now, when you get shrinkage values from a material supplier, they're typically given over a range, and that range is typically large. And it can vary based on many factors, including processing, the thicknesses that you use, the differences in the part geometry. So these are all things that simulation can help you with by determining what the volumetric shrinkage is of a part that will help reduce or eliminate mold modifications that you can make. Volumetric shrinkage is a result that shows the part as a percentage of the original volume. We designed it in CAD for a certain size, and after we went through the injection molding process, normally it's going to be a different size. And we're concerned about how different it is if it's going to meet our tolerances. So this plot is very important. We can utilize packing profiles to make the shrinkage more uniform across the part. We don't necessarily want the lowest amount of shrinkage if it means that we're going to have difference in shrinkage between the beginning and the end of fill. We want to have as uniform shrinkage as possible because we can machine a tool to be cut to that to shrink back to what we want within our tolerance limits. If you see a negative volumetric shrinkage, that normally indicates that there was expansion rather than shrinkage, and that normally indicates an overpacking situation, which could lead to ejection issues when you try to get the part out of the mold. Finally, large variation in volumetric shrinkage will contribute to stress issues, which will contribute to warpage issues. So you're going to have a different shrinkage in a different area, so the part is going to have to twist or compensate to make up for those differences in stress. So let's take a look at the software on a plot of volumetric shrinkage for our Fresnel lens. Here we have a volumetric shrinkage plot. Not too exciting because all we see is basically blue all around the outside because that's on the skin of the part. What we want to see is what's going on internally to see if it's different than the skin. So we can go up to the View tab, we can click on our cutting plane edit, and then we can choose a cutting plane that will be perpendicular to where we want to see. So for instance, if we want to maybe go through the sprue, we can do an XZ location, and then I'll turn the dialog off, and what we can see is a variation in shrinkage across the part. So thicker areas typically have higher shrinkage. And then we see thinner areas that don't, or have lower shrinkage. So if we were to go through and move this cutting plane by turning off the active plane, we can move this anywhere throughout the part to see what the volumetric shrinkage is in different areas of the model. And that's important for us because we want to know what areas are shrinking differently, because that's going to contribute to some of our warpage issues, if we have any. And speaking of warpage issues, we do have part deflection results inside of the software that can show you the dimensional distortion caused by the non-uniform change in internal stresses and how it relieves those as part of the injection molding process. Any dimensional differences that we have from the designed optical shape could cause quality defects in the optics that we want. We designed a lens for a certain shape, but it came out of the mold at a different shape, and that's not what we want. So anticipating those, or seeing them before we actually cut mold steel, will really save us money because the polishing involved with an optical tool can get quite high in terms of cost. So let's take a look at a deflection result display so we can see the total effects of deflection, and then also what each individual contributing factor is. Things like, is the shrinkage a problem? Is it a cooling issue? Or is it related to orientation? So let's take a look at that in the software. So here we have a deflection result for all effects for the part that we ran. Inside of the results section, you can go under the plot properties, and in the last tab, we can modify the scale factor of how it displays the results, because sometimes small deflections are very difficult to see. So if we can multiply them by a scale factor, we can see them visually a lot easier. Now, it doesn't affect the overall sizes, just the way they're displayed on the screen. So in this case, we're going to modify it by a value of 5. And what we see as we look at the part, I'm going to look at it from the kind of a top view. We can see some of those shrinkage results that we talked about before, from the original, and as it shrinks, to that 5 times scale. And you see that it's different in a flow direction versus a cross flow direction. And that's pretty typical for plastics to have different shrinkages in flow versus cross flow. And we can also see, as we look down the part, if we have any warpage that's different on the end versus the center, and we see that here. So if we look at it from a scale of, or on a side view, we notice that the sides are coming up more than the center of the part. So it's going to have kind of a rocking horse type of effect if we were to lay it on a flat plane or on a table. So that's important for us to know, because if we designed an optical part to have a certain focal point for a lens and it's off from that, it's not going to focus down on one area, but probably spread it out. And if that's not how we design the lens to be, that's pretty critical for us to know beforehand so we can make design decisions before we get to this point and have to make changes when we have to meet deadlines or have production. Now let's look at some results that are specific to birefringence. The first one being change in refractive index. This is a result that displays the difference between the refractive index after part deformation and relates that to the material's nominal refractive index. And the nominal refractive index is in the program's material database when you selected the material. This is used to qualitatively detect changes in refractive index that are caused by these in-mold residual stresses that remain in the part after deformation from the injection molding process. And if it isn't those, it could be the frozen-in stresses that are caused by the part cooling and deforming. Changes in refractive index of an injection molding part can vary dramatically over the thickness of the part. If the values are high, we have a few options. We can move the injection location to a non-critical area on the part. We can add a tab to try to remove those residual stresses that are very high near the gate, as you see in the image here. We can also alter our processing conditions such that we reduce the stresses in the part, such as increasing the cooling time or maybe decreasing the velocity so we don't have as high shear stress. We can also modify the geometry of the model so that the stresses are concentrated in an area that's not critical. So let's take a look at the change in refractive index plot in the software. Here we have the change in refractive index after warpage plot inside of the Insight software. And we can see that there is variation between the thick and the thin areas on the Fresnel lens. We can also take a cutting plane through the model and see some of the results through the thickness. So if we go in under View, edit the cutting plane, and put a particular plane inside of the model itself, we can rotate around and start to see some of the differences in the change in refractive index through the thickness of the model. And we see that they're pretty high near the gate, and in the thick sections, they're really concentrated towards the shear layer or just inside the frozen layer thickness. And that's pretty consistent throughout the part. So that's something that's very good for us to know, so that if we were to cut off this section of the gate, we'd remove a lot of those higher stresses or changes in refractive index that would cause birefringence. A couple of tips when looking at a change in refractive index plot. We can change the refractive index to look at tensors. And if the tensor has no axis along the direction of the incident of light, then unpolarized light may appear as a double image when you're looking through the part. That's something that we definitely don't want. If one of the axes of the change of refractive index tensor is parallel to the incident of light, no double image will appear, but instead the polarization of the light will change. So you see kind of a rainbow color typically. So the effect is proportional to the difference in the lengths of the two orthogonal components of the tensor. So when we look at a change in refractive index tensor plot, we can go in and typically the z direction is where the incident of light occurs by default. Now before we run the analysis, we can go under the advanced properties and change that to a different direction or set up a local coordinate system if we want to. Now let's take a look at that change in refractive index as a tensor inside of the software. In order to change the properties, we have to go under the Results tab, go to Plot Properties, and then in the first tab called Methods, we can go in and set up the tensors as axes. And by accepting that and hitting OK, now we can see that all of the results are in tensors. And in particular, in the high regions of change in refractive index, we can see how they align to the global axis, which is in the z direction. Another plot for birefringence that we can look at is the retardation of light. Now this result displays the absolute difference in terms of length between the phases of horizontally and vertically polarized light as it passes through the part from a direction named in the result. Now the default direction is aligned to the z-axis, but again, we can go in and change that value so that it's aligned to a local coordinate system or a different axis. The software automatically calculates the changes in retardation as an integral of the changes in the refractive index along the rays coming from that arbitrary direction. The value displayed is for the planes which maximize the phase difference, which is considered the worst case. A couple of tips when looking at the retardation of light result. Go in and adjust the plot scale by setting the lower limit to the part's maximum specified tolerance. For instance, values larger than 25% of the wavelength of the incident light will significantly affect the polarization of the transmitted light. A tolerance of 10% of the wavelength or even less is advisable in optically important sections of the part. Let's take a look at the retardation of light result inside of the software now. Here we see a retardation of light coming from the positive z direction result inside of the software. You'll notice that there are no results at the top of the part because that's where the light enters the part. Well, you can only see it on the back as the light comes through. And what we notice is if I look at the back of the part, is there are differences in the thin areas of the band as we look through the part itself. So what we want to do is scale this as we said before. So if we go under Plot Properties, Scaling, we can scale by a specified value and look at it from something like 0 up to, let's say, 1200 nanometers. So we'll go ahead and do that. And now we get a little bit more resolution inside of the part. So we can scale the plots based on our tolerances and see the differences in the birefringence, or in this case, retardation of light going through our Fresnel lens. A similar plot to the retardation of light is called the phase shift of light. Now the difference between this plot and the retardation of light is that this one is expressed in fractions of wavelength of light, where one cycle is 360 degrees and a wavelength of light we normally use green as a starting point, is 546.1 nanometers. However, we can go in and create a custom plot to see different results for different wavelengths of light. Some tips when looking at a phase shift of light plot. Adjust the plot scale by setting the lower limit to the part's maximum specified tolerance. Values of more than 90 degrees significantly affect the polarization of the transmitted light, and sometimes a tolerance of 30 degrees or even less is advisable if the part is optically important. So let's take a look at what the phase shift of light looks like inside of the software. Here we have the phase shift of light coming from the positive Z direction. And again, the first thing we want to do is go up to the plot properties and scale it such that it's within our tolerance. So we'll specify a scale. We'll change the value from 0 to, let's say, 180. And then see what that adjustment does. So if we look at this in terms of the bottom of the part, what we see are areas that are within that 90-degree range. So anything from the green to the blue should be okay. Anything that's beyond those, these areas that are see-through, or the areas that are in the green to red range, are areas that could be a problem for us in this optical lens. So to summarize, we can look at birefringence analysis results inside of the Autodesk Simulation Moldflow Insight software to help reduce risk in parts that we're building and catch things before they become problems. My name is Jaworski. Thank you for your time.